Hi, I'm Professor Harry Porter of Portland State University. In this series of videos, I will describe cache memory, and I'll introduce some of the basic concepts and terms and explain how they work. You've heard about L1 and L2 and L3 caches. After these videos, you'll understand what these terms mean. I'll talk about cache lines and cache blocks. We'll discuss what it means to be a cache hit or cache miss. I'll describe the principle of locality and tell you what a working set is and how it relates to caches. We'll talk about loop strides, we'll talk about cache coherency, and I'll explain how associative caches work as well as direct map caches. And then I'll put it all together and describe how modern caches work today. Here is the basic block diagram for any computer. On the left-hand side you see the central processing unit, and over here you see the main memory. From time to time the CPU needs data out of the memory, so it sends an address to the main memory, and the memory sends the data back. And periodically the CPU will want to update memory. It will do writes to memory as well as reads, and when it does a write it will send an address to the main memory as well as data to the main memory. Unfortunately, memory is relatively slow, and this is where cache comes into play. So the main idea of a cache memory is that it sits between the CPU and the main memory. The main memory is much larger than the cache memory, and it's also much slower than the cache memory. So the idea is that the cache can speed things up. The CPU, when it wants to do a read from memory, will send an address out, just like above in this diagram here, but that address will be intercepted by the cache. If the data the CPU is looking for happens to be in the cache, then the cache can return it immediately and quickly. If the data that the CPU is looking for is not in the cache, then the cache will go ahead and forward the address to the main memory. The main memory will then send the data to the cache, and the cache will forward it to the CPU. Now in this picture, notice that from the CPU's point of view, it looks exactly the same whether there's a cache there or there's not. In both cases, the CPU sends an address to the memory when it wants to read or write, and it either gets data back or it sends data to the memory. And it also looks the same from the memory's point of view. Okay? The memory is getting an address, and in the case of a read operation, it sends the data back. So cache can be added to the system, and it's somewhat transparent. So the CPU doesn't really have to be changed, and the main memory doesn't have to be changed. The cache is interposed, and basically it speeds the whole operation up. The main idea behind cache memory is that some data is important and it's frequently used, and it's critical that it be served to the CPU quickly. However, most data is not. Most data is not needed very often, and it's not nearly as critical. So the idea is that we keep the important data in the cache, and that way we can give it to the CPU much faster. There is faster access to the data that's more frequently used if we're able to keep that data in the cache. The less important data is still accessible, but it's stored in a much larger, much slower, and much cheaper memory. Caching is a very general concept. It can be used in a variety of contexts, and I've shown some of them here. Oftentimes when we talk about cache, we're talking about the cache that sits between the CPU and main memory. So this is traditionally what the cache is and what the word cache means. But we can have caches in other contexts as well. For example, we can put a cache in front of the disk memory or the flash memory. It sits between the computer itself, the CPU and the memory, and the non-volatile storage. So with caching main memory, typically we will read in chunks of main memory. We call these chunks blocks, and they're typically 64 bytes or something of that order. And so the cache is full of a number of blocks. Each block is 64 bytes, and from time to time it provides those blocks to the CPU. When we're caching pieces of the disk or the flash drive, then we're doing exactly the same thing, although the block size is much larger. In the case of caching disk or flash data, we typically call the items that we cache pages, but we also call them blocks from time to time. And they are pieces of files or pieces of virtual memory address spaces. And the size of a page that's cached here is usually quite a bit larger, and it's typically 4 kilobytes. Another application of the general idea of caching happens in your browser. Okay, so when you use your browser to look at some web page, you have to go out to the internet to get that web page, and that's a slow process. And so once the web page is retrieved, it's kept in a cache inside the browser, and the browser can refer to that page very quickly. It doesn't have to constantly go back to the internet to get that page. It caches it. Another example is also caching web pages, but here the idea is that your laptop is trying to get some web pages from a distant server that's perhaps on another continent. And so the communication time to this server on some other continent is really quite slow. So there are web servers that are on the internet, but they're much closer to you, maybe in the same city or maybe in the same region, certainly not on another continent. And those web servers will have copies of the web pages from the distant server. So when your computer asks for a web page, it goes out to the internet, but it doesn't go all the way to another continent. It just goes to the nearest server that happens to have that web page cached. In all of these cases, you see what's happening is the same. The main storage is slow, and the cache is a way to effectively speed that up. So we keep more commonly used data in the cache, and then that cache can provide that data to the client much more quickly. So we have the general concept of caching, which is applied to lots of different domains, and we have the more specific concept of caching that's applied to caching main memory by the CPU core. So typically this sort of a cache, and this is what we refer to when we hear the terms L1, L2, and L3. These caches are located on the CPU chip itself. So the unit that we're caching is usually a very small number of bytes, and it's oftentimes 64 bytes. So this is the block size, 64 bytes. The cache sits between a processing unit, that is a CPU core, and the main memory. And typically the main memory is much larger, perhaps 1 gigabyte. Now, the cache itself is a lot larger than 64 bytes. It might be, for example, 32 kilobytes or even 8 megabytes, but it's still a lot smaller than the 1 gigabyte main memory. These caches are located on the processor chip. So in a multi-core processor where you have perhaps 4 cores, you would have the cache sitting on the same chip as the 4 cores. Main memory is typically implemented with dynamic random access memory, which is cheaper and smaller than static RAM. Cache memory is generally implemented with static RAM, which is much faster. It takes more transistors per bit, so it's larger and therefore more expensive. So cache is small, expensive, and fast, whereas main memory is slow, cheap, and large. Here's a diagram showing the caches on the Intel Core i7 chip. So the dotted line here indicates what's on the main chip. And so you see the 4 cores that you would find on that chip, along with a bunch of caches, L1, L2, and L3 caches. Down here you have the main memory, which is not on the chip. It's on some other chip or chips. So the cores have their own private caches. The L1 and L2 caches are private to a particular core, whereas the L3 cache is shared among all of the cores. When a CPU core wants to fetch data, it is either fetching instructions that it intends to execute in the near future, or it's fetching data that it intends to operate on. And so the instruction stream is a little bit different than the data stream of data. So there is a separate cache for the instructions and the data. The instruction cache doesn't have to worry about updates because the CPU core doesn't modify instructions, whereas the data cache has to deal with writes, and that can make things a little bit more complex and difficult. Both of those get their data from the L2 cache, and that in turn gets its data from the L3 cache, and that from the main memory. So the L1 caches are small but super fast. The L2 caches are larger but not quite as fast. The L3 cache is much larger yet and slower still. And then finally the main memory is even bigger and slower. Here are some numbers to put this into perspective. For the Intel chip, the L1 caches are 32 kilobytes in size, and so you can see they're smaller than the L2 caches, which are 256 kilobytes. And the L3 cache is even larger at 8 megabytes. And then you can compare that to main memory, which might be 16 gigabytes, for example. Also, the L1 cache is much faster. Okay, you're looking at 4 clock cycles. L2 caches are slower, so you're seeing maybe 2 to 3 times slower. And the L3 cache is even slower than that, maybe another 3 times slower. And then main memory is even slower than that. In the next video, we'll get into some of the basic concepts and talk a little bit more in detail about how caches actually work. In this video, we'll talk about cache blocks, which are essentially blocks of bytes from main memory that are stored temporarily in the cache memory. We'll also talk about what it means for a cache hit to occur, or what cache misses are, and we'll talk about the eviction of blocks. We'll also get into a little detail about how the CPU interacts with the memory system on the system bus. The block is the main unit of data transfer between the main memory and the CPU. Typically, the block size is about 64 bytes, as it is in the Intel Core i7 chip. Note that I'm saying 64 bytes and not 64 bits. The register size is 64 bits, but the block size is much larger. So the idea is that the cache holds a small number of blocks, but these, we hope, are the frequently used blocks of data. The main memory holds a lot more blocks, and ideally these are blocks that we don't need quite as often. Now, when the CPU wants something from memory, it has to ask the cache, and the cache may have that data in one of the blocks that it's storing, or it may not. If the cache doesn't have it, it will have to go to main memory and retrieve the block. If the CPU only wants a small amount of data, for example, if the CPU only wants 1 byte, then if that byte is located in one of the blocks that are cached, then that's great. The cache can return that byte immediately. However, if the CPU wants a byte that is not in the cache, then the cache will go to the main memory and get an entire block. So the cache will then keep all 64 of those bytes in its memory, and that's generally a good idea because if the CPU wants 1 byte from a block, it's pretty likely that it will want other bytes from that same block. So that's why the system works well. We transfer data in large chunks all at once. We're transferring data in chunks of 64 bytes, which is great because those can be done much more efficiently than a lot of small transfers. Next, let's introduce these terms cache hit and cache miss. Let's say the CPU wants to read some particular block. We'll talk about writes later, but let's just focus on reading data for now. Well, there are two possibilities. Either that block is in the cache or it is not. If it's in the cache, then we have a cache hit. Okay, the cache contains that block. This is a good thing because then the cache can return that data directly to the CPU, and it can do that fast. So that's a fast access. However, the cache may not contain the block, in which case we have a cache miss. And this is bad because it's going to require some additional time to get the data. Okay, so cache hits are fast, cache misses slow things down quite a bit. So if it's a miss, the cache has to get the block from main memory. So the CPU asks the cache for a particular block, and if that block is not among the blocks that are stored here, then the cache has to ask the main memory for that. And the main memory will then send that block to the cache, and the cache can then forward the data to the CPU. Now, if there's a cache miss, then the new block will be fetched from main memory, and the cache will then store that block. So the new block will be saved in the cache, and that's great because the CPU may need to have other data from that block. It may need to access that block again in the near future, and so that block is now in the cache. But some other block had to be removed. The cache has a fixed amount of storage space, and so whenever a block is loaded from the main memory into the cache, some block has to be removed, and we call that eviction. So some block is chosen for eviction or replacement, and that block will no longer be in the cache. So future requests for a block that has been loaded into the cache can be served from the cache once the block is stored in the cache. But we also have to deal with the problem of eviction and replacing cache blocks. Let me talk a little bit about how the CPU communicates with main memory. The communication is done over buses, and a bus is really nothing more than a set of wires, of parallel wires, that are carrying data and control signals. And so I'm drawing the functional units, the CPU, the main memory, and maybe some other devices, as rectangles here, and these green lines down below are just wires. Okay? This symbol here with a little slash and a number indicates that this line represents not just a single wire, but 64 parallel wires. So the idea here is that 64 bits can be transferred between the CPU and the main memory. We talked earlier about transferring blocks of 64 bytes. Well, that would require a lot more lines, but in this particular example, I'm showing a CPU that can get 64 bits at a time from main memory. So the bus consists of several different components. One is the collection of lines that are the data bus lines, and then we have the address lines, and then we have some control signals here, some control lines, and I've shown two. One's called read and one's called write. And so in this particular example, it appears that our addresses are 48 bits in length, and our data that's being transferred back is 64 bits. So what happens when the CPU wants to read from memory. Okay, so read and write are a little bit ambiguous terms here. The CPU is reading, and so it sends some stuff out, and it sends the address out, and the data comes back. From the main memory's point of view, it's writing data onto the bus. So what for the CPU is a read might conceivably appear to the write, to the memory as a write operation. So I want to be clear that a read is transferring data from memory to the CPU. What happens when the CPU wants to read data? Well, it puts an address out onto the address lines. So the CPU drives these lines high and low according to the bits in the address. And it also drives the read request line high to indicate that it wants to do a read. Now I've shown just one memory component here on the bus, but there might be several different banks of memory. And I've also shown other devices. Here I'm talking about I/O devices, which also sit on the bus. And so all of these devices are looking at the address lines. So you can see the address lines flow into the memory and the other devices. And when a read request occurs, all of the devices that are sitting on the bus see that, and they check the address lines to see if it's one of the addresses that they contain. So main memory is mapped into certain addresses. The other I/O devices are mapped into other addresses. So the other devices are mapped into different addresses, and that's called memory mapped I/O. When the memory sees the address that it is supposed to take care of and a read request, then it responds by putting the data from that memory location out onto the data lines, and that data flows back, and the CPU then collects that data. In the case of a write, where the CPU wants to send data to the memory, the CPU puts an address out. It also puts the data that it wants to write out at the same time on the data lines, and it drives the write control line high. The memory sees the address, it sees it's a write command, so it picks up the data off of the data lines, and it stores it in its memory. Here I've just shown two control lines, the read and the write. In reality, things are a bit more complex. There may be some lines that are carrying the clock pulses. There may be also some lines that are controlling for the synchronization, and these are used when there are multiple devices trying to control the bus. In this simple model here, only a single device, the CPU, controls the bus, and other devices are essentially slaves and passive, and they just wait for the control lines to tell them when to do something. Here I've shown the same system with a cache added. The cache acts like a main memory from the CPU's point of view, and it acts a little bit like a CPU from the main memory's point of view. The CPU doesn't know whether it's communicating with the cache or with the main memory. Okay, and you might imagine that it thinks it's talking to the main memory directly. It sends out address line information, it sends out a command on the read or write line, and if it's a read operation, then it expects whoever it's talking to supply the data back after a certain amount of delay time. The main memory doesn't know that it's talking to the cache, it thinks it's talking to the CPU. So the cache basically acts like a CPU, and it can send address and read and write commands to the main memory, which then can supply data in the case of a read or accept data in the case of a write. So the cache can be added in the middle of this situation, and from the CPU's point of view it looks like a memory, and from memory's point of view it looks like a CPU. In this video we'll talk about why caching works so well, and that's because of the principle of locality and the idea of the working set. We'll also talk about the stride for programs that go through memory in regular ways. Most programs tend to execute the same small set of instructions over and over repeatedly. Typically, most instructions in the program are not used very often, but instead you have a few hotspots, and these are usually loop bodies. So the programs where execution is important typically execute a lot of instructions. Otherwise, their execution speed would be irrelevant. And those programs that execute a lot of instructions usually do that with loops, while loops and for loops and so on. And these loops tend to execute the same instructions over and over, and those are the instructions that are in the loop body. So here's an example, sort of short example of a program that has two nested loops, and the inner loop has a body with some statements in it, and those statements are executed over and over the most. So most of the time this program is executing the statements that are part of the loop body. And if you're a C programmer, you are familiar with this notation here. The loop test, the test for loop termination, and the increment of some loop index, those are also part of the loop body, because those tests and those increments have to be executed each time the loop executes. So this is a hotspot for the program, and we would hope that this area executes quickly. But since it's a small thing, it typically will only execute a small number of instructions and probably only access a relatively small amount of data. So while this program is running, it'll spend a long time in this loop here. Okay, so for a long period of time, only the instructions here will be executed. Okay, while the program is in that section of its behavior, while it's executing that loop, it's executing only these instructions and nothing else. So these instructions are part of the working set for the program at that moment in time. After a while, the program will change, the loop will finish, and it'll go off and do some other stuff, so things will change. Okay, but the working set is something that's defined at a particular moment in time, and while the program is in this loop, its working set will include the instructions that are part of the loop. And then later on, the working set will shift over time as the program moves on to other areas and executes different instructions. I just talked about a working set in terms of instructions, where you have a small number of instructions that are executed over a long period of time, and other instructions are not really used. The same is true of data. Some variables are used often and a lot, and other variables are used very rarely. So at one particular moment in time, a program will tend to access a small number of variables a lot, and it will tend to ignore most of the other variables. So from a data perspective, not an instruction perspective, this variable sum is a hotspot, because during this execution of the inner loop, this variable is both read and written, right? We're incrementing it, so we have to get the variable, and then we add something to it, and then we write the variable back. So this variable is in the working set when the program is in this loop. Of course, after a while, the program's behavior will shift, and it will move on to doing something else. As a result, the working set of data will also shift and change over time. The working set is a meaningful concept because most programs obey this principle of locality. This describes the behavior of many common programs. Now, there are some programs that are bizarre and weird, and they jump all over the place, and they do not exhibit the principle of locality. But by and large, programs, at least programs that are written by humans, exhibit this principle of locality. And what is that principle? Well, it says simply that if a byte of memory was used recently, it's likely that that byte will be used again in the near future. And if a byte of memory was used recently, then it's likely that nearby bytes are going to be used in the near future. So we can break these down into two different kinds of pieces and call one of them temporal locality, that is nearness in time, and the other is spatial locality, that is nearness in space. So if a byte of memory was used recently, it's likely to be used again soon. That's temporal locality. And if a byte of memory was used recently, then bytes with nearby addresses are likely to be needed again, and to be needed soon as well. And that's the principle of spatial locality. But these are both aspects of the more general principle of locality, and it applies to both data and instructions. Most programs exhibit locality both for their data usage and for their instruction fetching. Now we're ready to try and give a definition of the working set. We can say it's the set of bytes that were used recently, whether data or instruction, we don't care, but just the set of bytes that the program needed in the recent past. Another definition might be the set of bytes that will be needed soon in the near future, although we can't really know what the program's going to do, so it's kind of difficult to know what bytes are going to be needed. But generally, because of the principle of locality, these two sets are really quite similar, so there's a lot of overlap. So we can try to identify the sets that were of bytes that were used recently, keep those in memory with the assumption that the related bytes will be needed again soon. So the idea behind the working set is that if the working set can be kept in the cache where access is very fast, then the program will run faster. So the idea is we try to keep the set of bytes that were used recently in the cache as well as bytes that are nearby, and that way the set of bytes that we might need soon will be in the cache already. So when we bring bytes into the cache, we keep them. We try to keep the bytes as long as possible, of course, but the cache has limited memory, so occasionally we have to evict some bytes, but we prefer to keep the most recently used bytes in the cache. So when we bring in bytes to the cache, we also bring in nearby bytes, bytes that are close to those bytes that have similar addresses. That's because when we fetch, say, a byte of memory or a word of memory, we bring in a whole block of bytes. So when we fetch 1 or maybe 4 bytes, we end up bringing in 64 bytes into the cache, thereby loading in nearby bytes that might be needed in the future. A program's working set changes over time. So let's take a look at this program, and here's a timeline. At some point, we start the program executing, and it executes for a while until ultimately the program terminates. If we want to look at a section of the program's execution, we can look at a window of time, an interval of time. This might be 1 millisecond or whatever. We don't know. And we can ask which bytes were used during this window of time, and we can define that as the working set. If those bytes were all in the cache when they were needed, then the execution of the program was fast. There were no cache misses. Everything was in the cache. And so our hope or our goal is to get the entire working set into the cache at all times. Of course, this is not achievable in entirety, but we can come close. So we want to try to get as much of the working set into the cache as possible. But as the program advances, the window moves, and so what's the working set in this area of the program's execution? Well, it's one set of bytes, but later on the program's doing something different and it needs another set of bytes. So the working set shifts over time. We can also ask about how big the window is. How large is this window? We might measure it in terms of the number of instructions that are executed. Perhaps the instruction executes perhaps the program executes 1 billion instructions from beginning to end. Well, how big is the window size? Maybe it's 10,000 instructions, or maybe it's 1 million instructions, so it's a larger window. Obviously, if we look at a larger number of instructions, the working set is going to increase. The number of bytes accessed by 10,000 instructions will be smaller than the number of bytes accessed by 1 million instructions, most likely. Okay, you execute more of the code, you're going to touch more of the data, you're going to touch more instructions. So as you increase the window size, the working set gets larger. So the idea of the working set is more of a concept. It's not a rigorous, rigid definition. If you look at a larger window, you're going to see a larger working set. It would be nice to have larger caches to hold bigger working sets in memory, but you can't always hold as much as you want to in the cache. So you try to put as much into the cache as effectively as you can, given you have a fixed cache size. We can also look at what happens to the working set size as we look at more and more of the program. If you increase the window size all the way to include the entire program from beginning to end, then there's some maximum amount of bytes that program needs to access in order to run to completion. Maybe it executes all of its instructions. Maybe it touches all of its data. So there's some maximum. But as the window size gets smaller, it needs fewer and fewer of the bytes. And in the sort of the limit, when you're looking at just one instruction, well, you don't need very many bytes at all. You need the bytes that comprise that one instruction, maybe 3 or 4 bytes, and maybe that instruction touches a word of memory, so you need 4 bytes of data from memory. As the window size increases, the working set size also increases. So there's no magic point, no magic size for the working set, but we like large caches so we can get more of the working set into memory. The principle of spatial locality says that nearby bytes are likely to be accessed soon. And so let's look at an example of how this applies to data. Here's a little program that has a loop, and it does some stuff in the loop body, and among other things, it looks at an array. And it goes through this array, and you can see that it's going through this array sequentially. So since it touches every element of the array in turn, we say that it has stride 1. Okay, so it's going through the array, element by element. So how is this array stored in memory? Well, here on the left I show more schematically that the array is stored with one element directly after the next. So A0, A1, A2, A3, and so on. Now, each one of these elements may take several bytes, so perhaps this is an array of single precision floating point numbers. Each one of those takes 4 bytes. So here's another picture of memory showing the contents of this array. And here you see I've shown addresses for each memory location, as well as the byte that's in that memory location. And so here we have a group of 4 bytes, here we have another group of 4 bytes, here we have another group of 4 bytes. So the array is stored one element after the other. This program is going through the array element by element. Each element is 4 bytes long. So it's going to access this group of 4 bytes, and then this group of 4 bytes, and then this group of 4 bytes. But it's going, we say it has stride 1 because it's going through the memory in order and not skipping anything. Now let's look at this program, which is similar, but in this case we are incrementing the index by 4 instead of by 1. So we're going through the array by 4. In other words, we're accessing element 0, then 4, then 8, then 12, then 16. So we say that this program has a stride of 4. It's not so good. With a stride of 1, when we bring in this byte or these 4 bytes to access the first element, it's likely we'll bring in the nearby bytes for maybe elements 1 and 2 and maybe 3. And so we bring in bytes that are nearby, and since we're going through the program with stride 1 in this first program, we're going to have a lot more hits where the data that we want, it has already been loaded into the cache. In this program, we are jumping through memory, so we bring in nearby bytes, but we don't necessarily use those nearby bytes. And so consequently, this program is not going to perform as well, even though it may have the same number of iterations total. It's going through the memory with a stride of 4 rather than a stride of 1. So the second program has less data locality. The next item is consequently less likely to be in the cache, so we'll have a higher rate of cache misses and consequently poorer overall performance. Now let's take a look at a two-dimensional array. Here I've drawn the array the way you might visualize it. You can see it has 3 columns and it has 4 rows. And the array elements are 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, and so on. How is this thing put into memory? Well, the programming language C and many other programming languages use what's called row major order. In other words, they store this row all contiguously in memory, followed by the next row, followed by the next row, followed by the next row. So here I've put this array in memory. In other words, I've taken this two-dimensional array and linearized it. And so we see that the first element A00 is stored, and after that comes element 01 and then 02. In other words, we store all of this row, which we can call row 0, and then we follow it by row 1 elements, so the 3 elements in row 1, and so on. So that's row major order. There's also something called column major order, which is to store all the columns one after the other. But most programming languages use row major order. So here's a piece of code that goes through this array. And it's a two-dimensional array, so the programmer has coded it as a doubly nested loop. So the inner loop, I've circled in red here. It accesses an array element, and the first loop iterates I. I is the row number, and the second one iterates J, the column number. So this thing goes through the array elements in this order: 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2, and so on. So it's going through it in row major order. You can so it will access the data elements in this order: 0, 0, 0, 1, 0, 2. It does the first row. Okay, I is the row number. It does all of row 0. For I equals 0, it does all of the J's, 0, 1, and 2. And so it does all of the J's. And then it goes on, increments I to the next row, and it does row number 1. And it increments J, 0, 1, and 2, and does all of row 1. And then it does row 2, and then row 3. So this program is well behaved. It goes through memory in order. it has a stride of 1, and it's going to have a lot of cache hits, and it's going to be well behaved. Here is a similar program. Okay, it touches the same array elements, but it just does them in a different order. You see that I have kept the I and j in the same order here, but I've reversed the loops. So this one will do all of j equals 0, and it will vary I more frequently. It will vary I more frequently. So when j is 0, it'll do I 0, 1, 2, and 3. So it goes through the array this way in a column order, and then it moves on to the next j, j1, and does 0, 1, 1, 1, 2, 1, 3, 1. And then it moves on to the last j equal 2, and does I0, I1, I2, and I3. So it's going through the array, all of the same array elements, just in a different order. So how does it do it? It goes through 0, 0 first, and then it goes to 1, 0, and then it goes to 2, 0, and then it goes to 3, 0, and then it comes back and goes to 0, 1. So it's jumping around a bit. Okay, so this one has a different stride. And since it goes from 0, 0 to 1, 0, we can say that it has a stride of 3. Now each of these may be 4 bytes or 8 bytes, so it might make more sense to talk about how many bytes it's skipping over. In this small example, it's possible that all of our data will fit into a single block and all be in cache from one load, so it may not make any difference. But where this really counts is when you have gigantic arrays with lots and lots of elements. Let's look at an example that's maybe more realistic. So we'll assume that our cache block size is 64 bytes. Each double precision floating point number is 8 bytes. So what this means is each cache block can hold 8 doubles. And let's imagine we've got just a really enormous array. And here I'm showing just a fragment of the array. Here's part of row 293, and here's the first part of row 294. Each one of these rectangles is supposed to be 8 bytes, so it can hold one double precision number. And since each block holds 8 doubles, the blocks are fairly small, like this. So let's imagine that we've got a nice, well-behaved program that has a stride 1 access. In other words, it's going through the memory in sequential order. So when it reads a double, so say when it moves from row 293 to row 294, it might read this double right here. When that occurs, that's going to cause this cache block, the entire block of all these 8 double precision numbers, to be loaded into this cache memory. So when the program tries to read one element from the array, it pulls in all 8. It pulls in 7 additional elements. And since it has a stride 1 behavior, it's going to then access those elements next, and those will already be in the cache now. So the first element will cause a cache miss because it's not in the cache, and we pull that block in, but the remaining 7 accesses will be cache hits. So we have 1 cache miss for every 7 cache hits. So we can define the cache hit ratio and the cache miss ratio as how many hits we have out of the total number of accesses. So in this case, just looking at what it's doing to the array, we see that it has a cache hit rate of 7 out of 8. Okay, that's about 87%, 87.5%. The cache miss rate, and unfortunately this thing misses 1 out of 8 times, or 12.5%. So you can see that this is a pretty good, well-behaved program. In this video, we'll go into a little bit more detail about how caches are organized. We'll also talk about the problem with writing to the cache and what cache coherency is all about. With main memory, we have a sequence of bytes, and the memory stores the bytes, but the addresses are not stored. The addresses are implicit. I indicate that in my drawing of memory here by showing in black all the bytes that are stored, one after the other. And over here in green, I indicate the addresses in hex. You can tell it's hex because there's an A and a B. And these addresses are more or less implicit. We don't have any bits of storage taken up by storing the addresses. In the cache, we have a number of blocks, of cache blocks, and those cache blocks could have come from anywhere in main memory. So here's a picture of the cache, and it's sitting between main memory and the CPU. And in this particular example, my cache has only 4 blocks in it. And each block, well, in this limited example, they only contain 8 bytes. And the cache blocks have to somehow be labeled with addresses to show which block these 8 bytes are. So here in this, I've outlined, or at least tried to outline, 8 bytes. Okay, 0, 1, 2, 3, 4, 5, 6, and 7. And those bytes are currently the exact same bytes that are held in cache. So this block is being held in the cache memory. The bytes are still in main memory, of course, and as long as there are no writes to any of these bytes, then the values are exactly the same. We need to associate with each block some additional information to tell where these bytes are coming from. So for the entire block, we need to have the address of where that block begins. Okay, so here's a block of data. It comes from this area, and it's the 8 sequential bytes that start with that address. Here's another group of 8 bytes. I haven't actually drawn in the bytes, but they would, of course, be there. And we have an address for it. So that's another block, and we have some other blocks as well. So the point I want to make here is that the cache has to store additional bits beyond just the data itself. And in this simplified world, it's got to at least store the address of where that block comes from. So next, let's turn to the problem of writes. But before we do that, let's talk about a read. If the CPU wants to read a particular byte, then it may or may not be in the cache. If it's in the cache, of course, we call that a cache hit, and if it's not, it's a cache miss. And in the case of a cache miss, the cache needs to read the block from main memory, but in order to have some place to put it, it has to evict a block that's already in the cache. And ideally, we'd like to evict the least recently used block. And many caches can actually implement that exact strategy. So we will evict the block that was used furthest in the past, with the hope that it is the least likely to be needed again in the near future. Now, what happens if the CPU wants to write to memory? Well, there are, again, 2 possibilities: that the cache contains the block or the cache does not contain the block. If the CPU wants to write a byte and the block containing that byte is in the cache, we call that a write hit. Okay, the cache contains the data that needs to be modified. And if the cache does not contain the data, if it doesn't contain the block that has that particular byte in it, then that's a write miss. Well, let's look at the hit first. So the cache contains the block. There are 2 different approaches that a cache can take. One is called write through, and the other is called write back. These are design decisions that are made when the cache is designed in the first place. And so it's not like the cache is going to sometimes switch midway. Once it's manufactured, it's going to be either a write through cache or a write back cache. Same with the write allocate and the write no allocate. These are design decisions that are made at the point the cache is designed and manufactured. With write through, okay, the cache contains the block, that's getting updated. What happens here is that the cache unit will immediately forward the update to main memory. So the cache will write the modified block with the modified data back to main memory immediately. It won't wait. On the other hand, with write back, the cache will wait. So what happens is it updates the data that's stored in cache, right? The cache contains the block that's being updated, so the byte in that block is updated, but the cache does not copy it back to memory. So the block that's stored in memory, the version of the block that's stored in memory, will have the old data in it. At some later time, the cache will ultimately have to write that block back to memory. And when does that occur? Well, it occurs when that block is evicted. So sometime in the future, the cache will need to read a new block from memory, and it will choose this updated block to write back to evict, and it will have to write it back to memory. It can't just discard it. If the block has been updated, it needs to be written back to memory. Now, if the write is to a block that's not in the cache, if the cache doesn't contain the block, then there are two choices called write allocate and write no allocate. So with write allocate, the idea is the cache will read the block from memory and put it into the cache and then update the copy that's in the cache. It will update the block as it's stored in the cache. With write no allocate, sometimes called no write allocate, the cache will not load the block into the cache memory, but instead it will just forward the write right on through the cache to the memory. So it will update the data in memory, but it will not copy that block into the cache. Which of these strategies do caches actually use? Well, typically they do this. On a write hit, they use write back, and on a write miss, they use write allocate. Okay, although the other alternative sometimes happens. So when there is a write hit, in other words, the CPU wants to update a byte, and that byte belongs to a block that's already loaded into the cache, then it updates the copy in the cache, but it doesn't immediately notify the memory that that cache block has changed. So it doesn't copy that update through to the memory. Instead, it saves it until later, okay, when the block is evicted. And when a block is evicted from cache, if it's been updated, it has to be written back to main memory. But if it hasn't been updated, there's no need to write it back to main memory, and that would just waste a bunch of time. So the cache also maintains what's called a dirty bit for each block. So this is a 1-bit flag that's associated with each block in the cache. Each block has a bit called this dirty bit, and it's either 1 or a 0, or 1 indicates that it's dirty, that is, that the block has been modified. In other words, there's been a write to some byte within the block. That block is no longer a virgin, it's now dirty, so to speak, and it has to be written back to main memory. If the dirty bit is 0, then the block has not been modified, and it does not need to be written back to main memory. Okay, so we can save the time that would be wasted writing it back to memory. Okay, and coupled with this, it's typical to use write allocate for a write miss. So if the CPU tries to modify a byte but that byte belongs to a block that's not in the cache, then what the cache will do is it will allocate. Okay, in other words, it will load the block into cache. Obviously, it has to evict some other block, but after it does that, it loads the block into the cache, and then it can perform the write, and it performs the write on the cache version of the block. Okay, it doesn't update memory immediately. It doesn't let memory know. It does not write through. So it has to set the dirty bit to indicate that that cache block has been modified. And it doesn't immediately update memory. Instead, it waits until the block has to be evicted. And this is a pretty good strategy, particularly if there are more writes to this block. And we know from the principle of locality that if this block is touched, it's likely to be touched again. And so if it's written to, it's likely that this block will be written to again. And since it's already in memory, that's a good thing. So this is what's typically used. On a write hit, we use write back. Okay, in other words, we don't write back immediately, we wait. We set the dirty bit and do it later. And on write miss, we move that block into the cache and set the dirty bit. And then later we update memory. There's another approach, though, that's also used, and that is to write through. So when the cache contains the block, it's typical just to go ahead and modify the memory. And likewise, these two tend to go together, that when there's a write miss, we're trying to update a byte that's in a block that's not cached, the cache will just forward the write request on through to the memory and not bother to allocate a block of the cache to that. So the write is just passed through. By the way, the first strategy tends to keep updates in the cache without notifying the memory immediately. So the memory may be somewhat out of date. Whereas with the second strategy, memory is notified as soon as possible, and so memory is not out of date. The data in memory is reflecting the writes that have occurred. In a computer situation where you have shared memory, where you have multiple CPUs and they are sharing memory, there can sometimes be problems if there are inconsistencies. For example, if one CPU tries to write a byte of memory and that byte is not updated in memory, it's only updated in the cache, another CPU might try to read that byte and see an old version of the data. So the write through, no write allocate strategy might make more sense, might be necessary in a system where you have several CPUs sharing main memory. On the other hand, there are other better ways to synchronize between multiple processors, so this may not really be a valid reason to use these strategies. Now let's take a look at what a cache line is. In this example, I'm going to assume that our cache blocks are 8 bytes in length, not 64 bytes, but only 8 bytes, just to make this a little bit more manageable. And let's assume that our addresses are 32 bits in length. So each address has 32 bits, and the address of a block will always end in 3 zeros. Okay, we will assume that blocks are aligned, so every 8-byte aligned block of data will have an address that ends in 3 zeros. And the individual bytes within that block would be 0, 1, 2, 3, 4, 5, 6, or 7. In other words, in binary 0, 0, 0 through 1, 1, 1. So the block address will end in 3 bits because the block size in this example is 8 bytes. If the block size were larger, it would be more bits. If the block size were, for example, 16 bytes, then the last 4 bits would be 0. If the block size was 64 bytes, then the last 6 bits would be 0. But in our example, it's just the last 3 bits because blocks are 8 bytes. So this is a cache line here. Okay, it's said to be 8 bytes in size, although we've got additional information about which block it is, as well as some bits. You see here I've got a dirty bit. So the cache line contains the 8 bytes of actual data that came out of memory. And so here we have in hex 8 bytes of data. So this is the byte that's at the beginning of the block, and the next byte, and the next byte, and so on. So we have the 8 bytes from memory. So this is a sequence of 8 bytes in order out of the main memory. And where do they come from? Well, that's the address of the block itself. So in this case, looking at this bit pattern in hex, we have A, C, B9, B9, 3, 5, 3, 5, and 9, 8. Okay, and so you can see that the last 3 bits are 0 because the last hex digit is 8. So we might not actually need to store those last 3 bits because they must always be 0. So we might actually only store 29 bits and not all 32 bits. So in any case, we have the address of the block, and then the addresses of the bytes within that block are implicit. We don't need to store anything there. We've also got the dirty bit. Bits are either 1 or 0, and one value indicates that the block is dirty, that is, that it's been modified, and we need to write it back to memory at some future time. And the other value of the bit indicates that it has never been modified, and so we don't need to write it back. I'm also showing another bit called the valid bit. Is this line full of data? In certain situations, we need to know whether these bytes are valid or not. For example, when the computer first powers up, all of the memory will have values, random, unpredictable values, to be sure, so we can't rely on those values. So by setting the valid bit to indicate this is not a valid line of data, not a valid block of data, we can avoid using it and force the system to load the block from memory. These valid bits are also used when there's a context switch and we switch from one address space to another. That's beyond the scope of this talk, but when the operating system moves from one thread or from one process to another thread or another process, there's a different address space. And so the contents of the cache apply to one process and not to another process. So because of virtual memory, these addresses are all messed up. And so the solution is just to set all the bits, all the valid bits to 0 to indicate that none of the cache is valid. Then as the process starts up, the cache is said to be cold, okay, meaning it doesn't contain any useful data at all. A cold cache contains no useful data, and we can make the cache cold by setting all the valid bits to indicate that every cache block is invalid. And when the process starts up, immediately we'll have a lot of cache misses, and so initially we'll have to load blocks of data from the memory into the cache, but once the cache is warmed up and full of good useful data, then the program can proceed. So warming the cache up basically gets the working set into the cache so that the program can then run at full speed with a much lower miss ratio. In this video, I'll describe how fully associative cache memories work. Before talking about associative caches, I want to describe associative memories. Here's a traditional memory. Okay, the idea is this dashed outline refers to a single chip or maybe a memory module. Inside of that, you've got the data, which is in black, and it's a sequence of bytes. Each byte has an address. The address is implicit, but they start at 0 and go sequentially 1, 2, 3, all the way up to some maximum. In this case, I've got a maximum of 16 bits, so I can say that this is a 64K memory address space. But regardless of whether it's 32 bits or 16 bits or whatever, the idea is that an address can be fed into the memory unit, and in the case of a read operation, the data will come out of the memory. So the address goes in, the addresses are implicit, all the addresses are there. There's a byte for every single address, so regardless of what address you put in, you will get a data value out. Now with an associative memory, these things are a little bit different. The idea is you've got a key and a value stored. So you've got a bunch of pairs. Each pair is a key and a value. So each one of these lines has both a key and a value. And to use this, for example, for a read, you put a key in and a value comes out. It may come out. Not all keys are present. Okay? In the case of a normal memory, it doesn't matter what address you put in, there is a byte there for that address, so something will come out. And in this case, you've got 64,000 different bytes, so something will come out because you've only got 64,000 different addresses. With an associative memory, the keys may be much larger. You may not have very many lines, and typically these things don't have very many lines. They might have 16 or 32 or maybe 512 lines, but they don't have 64,000 lines. All of these lines are searched in parallel for a match. So the key goes in and a match is made, and if a match occurs, then the data may come out. But you can also have another result, which is that there is no match. Here I happen to have shown the keys to be the same size as these addresses here, but the keys can actually be any size. They can be much larger. So with the traditional memory, the addresses have a certain size. For example, they might be 16 bits as they were in my previous example, and in such a case you would have 64,000 different values stored. In general, you have 2 to the n values in the memory. With an associative memory, the key can be any size at all. It might be, for example, 29 bits or some other number. And we also have a small number of lines. Here I'm showing the lines running across like this. So here's a line, and we have a small number of lines in a typical associative memory, maybe something like 32 different lines. We've got the key stored in one part of the line, and we've got the value stored in another part of the line. And the associative memory works like this. The hardware works like this. You've got a bunch of wires running up, okay, shown in green here, and they deliver the key into the chip or into this part of the chip, into this hardware. And you've got other wires running down here like this, and this is where the value comes out. Okay, so we've got a small number of lines in the associative memory, and the key goes in. So if we have a 29-bit key, for example, we'd have 29 of these wires here. And so the key goes in here, and in parallel, those signals propagate all the way through the associative memory. And each line will match or try to match its key against the values on those wires. So the key goes in, it's carried to all of the lines by these parallel wires, and all the lines in parallel will look to see whether they happen to match. And if one line matches, then that line will stand up and wave its arms and say, yeah, it's me, I match. And so what will that line then do? what it will do is it will drive these wires here, these output wires. So I don't know how big the value is. Well, for a cache, the values will be blocks of data. So we might have 8 bytes or maybe even 64 bytes. We have a bunch of parallel wires coming out. So the matching line drives these wires. The other lines don't touch the wires. They don't put any values onto the wires. And so a key, perhaps 32 bits, goes in, a match is found, and the value comes out. So with a cache memory, with a fully associative cache memory, the key is the address of the block, and the value is the block data. Maybe it's 8 bytes, maybe it's 64 bytes, but usually it's a fairly large amount of data. And so the address of the block goes in, and if that block is stored in the cache, then the data from that block comes out along these wires here. Now let's look at an example that's a little bit more realistic. This is an example of a fully associative cache. We're going to look at an example where the block size is 64 bytes, so we can denote that B, and the number of lines in this associative memory will be 512 lines. And so therefore, the size of the cache is the block size times the number of lines in the associative memory, B times L. In this case, it's 32 kilobytes. Now, this is only the block data that's in each line. There's also the key and maybe some other bits like the dirty bit or the valid bit. We don't include all those other bits. We just include the data bit when we're measuring the cache size, even though more bits are actually stored. So when we say 32 kilobyte cache, we're saying that the block size times the number of lines is 32 kilobytes. And we've just got one set, so this is a fully associative cache memory. We can say it's a set associative cache memory with only one set. And let's look at an example where our addresses are 32 bits in length. In more modern processors, they might be 48 bits or 64 bits. But for this example, we'll use 32 bits. And each address then consists of two parts. We've got what we call a block offset. That's going to have to be 6 bits. We need to address a particular byte within the block. These blocks have 64 bytes, so since 2 to the 6th is 64, we need 6 bits to select which byte from the block. So this is a number ranging between 0 and 63. It picks out the block in the byte, and that's the block offset. The remainder of the address is going to be the key. And so we've got 32 bits minus the 6 leaves 26 bits. And this key we also call a tag. Okay, so we've got a 26-bit tag. Let's talk about how this fully associative cache will operate. Now I'm presenting it sort of like a program here, but keep in mind the cache is all hardware. Okay, it's meant to be extremely fast. So all of the stuff I'm about to tell you about will happen in hardware, so will happen within just a small number of clock cycles. So the cache unit is a hardware unit that takes an input, and that input is an address. In our example, we're looking at 32 bits. So the first step is to separate out the tag from the offset. Remember that the offset is 6 bits and the tag is 26 bits. And the cache contains an associative memory. It's got 512 lines in it. Each line has a key and a value. The key is a 26-bit tag, and the value is a 64-byte block of data. So in the second step, we send the 26-bit tag from the address to the associative memory, and from that we either have a match or we don't. And if we have a match, then the block data from the matching line comes out. So we retrieve a 64-byte block of data from the associative memory. If we find a match, then that means one of the lines in the cache has a key that matches this tag from the address. And so if we have a match, 64 bytes come out. The data from that line is fed out, and the cache system then uses the 6-bit offset to extract the desired byte or bytes, and it sends those onto the CPU. If the associative memory does not contain a line that matches, in other words, if the keys for all the lines are different than the 26-bit tag, then there's no match. So at that point, the cache hardware has to select a block from the associative memory to evict. And the cache is going to select the least recently used block, least recently used line of memory, and it's going to evict it. Now, we haven't really talked about how we implement the least recently used algorithm, but we would obviously need a few more bits to detect which one is least recently used. And furthermore, we'd have to update those bits every time we use a block. But I'm not going to talk about that. But assuming the cache hardware can figure out which block to evict, it then will ask whether the dirty bit for that block is set. If the dirty bit is set, then that block has been modified, and it needs now to write that data back to memory. So it has to take a timeout, so to speak, and take the extra time to copy the block data back to memory because it's been updated somehow. And after that, it then will send the tag value from the address, the 26-bit tag value that we got out of the address, to the main memory, and the main memory will respond by sending 64 bytes of data back, and at that point the hardware can update that particular line in the associative memory. So it needs to update the key portion, the data portion, as well as clear the dirty and set the valid bits. Also reset any least recently used bits as well. At the same time, the cache hardware will extract the byte that the CPU wants back. So it will use the offset from the address to extract the byte of interest, and it will then send that byte on back to the CPU. So that's a fully set associative cache memory. We've got just one set, and the entire cache is stored in the lines in that fully associative memory. In the next video, we'll look at direct mapped caches.